Good morning. Welcome to all of you to the second part of INdAM Day. Yesterday, we said that this is an unusual INdAM Day, but only into organization, because the level of the talks, the level of the speakers is very high, and yesterday was a very nice afternoon, scientific afternoon. I hope that today it will be also at the same, but there is no problem, I think. And again, thank you to the speaker for accepting our invitation. And again, thank you to the technical staff of INdAM for the technical support. Welcome again. And please, Filippo, you can introduce the first speaker.
Thank you, Gioconda. So good morning to everyone and welcome. So I'm very honored and happy to introduce Nuria Fagella from University of Barcelona. So Nuria got her PhD in Boston in 1995 with Robert Devaney. And she's interested in dynamical system and ergodic theory and function of a complex variable, and more generally global analysis and analysis on manifold. So in fact, her field of interest is related to dynamics of entire transcendental maps and quasi-conformal surgery, complexification of analytic circle diffeomorphism, space of exponential family, and especially those having Siegel disk and Baker domains of transcendental maps. Also, she studied Hermann rings of meromorphic maps. And she applied quasi-conformal surgery as a mean to attaining maps between parameter spaces, mainly polynomial parameter spaces. She advised, at least as far as I know, 5 PhD students up to now. And she published in top journals like Invenciones, Transaction of AMS, Communication Mathematical Physics, Advances in Mathematics, and many others. She gave, in fact, many contributions to long-standing and outstanding problems in dynamics. Here I wish to just recall one of her contributions. In 2014, she solved together with Baransky, Jark, and Karpinska a long-standing conjecture, which is it true that the Julia set for transcendental Newton maps is connected? And the answer is yes, and this comes from her work. And the main result there is that transcendental maps with disconnected Julia set must have at least one weakly repelling fixed point. But aside proving this result, this work completely changed the perspective in the problem and the field, because was one of the first, and probably the first one, where they work introducing the tool of hyperbolic geometry in this field. Aside being a great mathematician, Nuria is also a great person. She's very gentle, she's very optimistic, and I mean, she really likes to do mathematics and to explain things. I know at least 2 Italian mathematicians, in fact 2 young women, who continue to do research, and especially research in holomorphic dynamics, because they attended some of her lectures and they were so enthusiastic about the presentation and about the matter that they decide to continue in this way. So I'm very proud and I'm very happy to have here Nuria today. And I'm pretty sure, well, I also have to mention that she's very clear, and she will make a really, she does a really very good talk. And in fact, most of the time, her presentation is so clear that people don't even believe how hard is what she's doing. So in any case, I'm very happy to introduce Nuria. And you know that after the talk, I can read your question on YouTube, and I will ask for you the question to Nuria directly. So, so Nuria is going to talk about complex dynamics, a meeting point between topology and analysis.
Okay, Filippo, so thank you for such a beautiful and nice introduction, and I hope not to disappoint you after all these expectations that you have created. So let me try to share my file with you. Oops, sorry. 1 second. Okay, is it visible? I hope. So as I said, thank you very much for this beautiful introduction. Thank you very much for inviting me. It's always, I could say it's always a pleasure to come to Italy and visit. Unfortunately, this time the talk comes without a visit, but anyway, I'm impressed by the level of professionality in this INdAM day and how well organized it is, and interesting talk. So I hope to keep the standards as high. So as Filippo mentioned, I'm interested in holomorphic dynamics in iteration on the complex plane. And since this is for a general public, I will try to give you a feeling of what this is about. And I chose a problem, or at least a threat, that I thought might interest more than people in more than one area, right? And it's also related to work that it's done here in Italy by Filippo, actually, in many occasions. So, okay, wait a second, why doesn't this go through? Here. So indeed, we are interested in iteration of holomorphic maps, right? We will today only do it in C, but you can do this on the sphere, you can do this on the sphere -1 point. So there are several places where iterating makes sense. In dynamical systems, in discrete dynamical systems, so this is not differential equations, this is iteration. So we are interested in the asymptotic behavior of orbits, which means you take an initial condition, you apply F repeatedly, this gives you a sequence, and you want to know what happens when n tends to infinity for this type of sequences. And the motivation for doing that is manifold, right? So the first one, in fact, I would say the first one historically is a root finding algorithm. So when we do something like Newton's method, which we all know what it is, it's you are iterating, and the natural place to look for to iterate Newton's method is actually the complex plane, because that's where all the roots of the polynomial or of the function that you are looking at lie, right? I'm talking about the real map complexified. So Newton's method, in fact, was what motivated all this theory, because it was only studied locally already in the 1900s, or even in the 1800s, Cayley, Hamilton, and then Julia and Fatu later on in the 1900s started, motivated by this, started a general theory of what does it mean to iterate a complex function. But still, apart from the usefulness of the discipline, there is also the beauty of the discipline, right? So of the area. So this is an area that has attracted mathematicians from every other field, because of the many tools from many different places that come and meet together in holomorphic dynamics. So you can talk about topology and complex analysis maybe as the two main ones, but also arithmetic, geometry, and this is like an infinite source of interesting problems. So not only it uses the tools from all these areas, but it just provides these areas also with a lot of interesting questions and challenges. So you can really come from any of these areas and find something interesting to do in holomorphic dynamics. That's how I see it, at least. Here, for example, is the Newton's method that I was talking about, looked in the sphere, because this is Newton's method for polynomials is a rational function, so it makes sense to study it in the sphere. And here you have one with 3 complex roots, so that every color is a set of initial conditions converging to one of the 3 roots. And you see, you can start seeing here how these basins of attraction really distribute very interestingly in the plane with these fractal boundaries, etc. So this picture is like a representing picture of what it is to iterate a holomorphic map. So the characteristic or the feature of holomorphic iteration that makes it different from iterating a non-analytic map somehow is this basic partition of the phase space, right? So the complex plane decomposes into two totally invariant sets. It's like if you were talking about two dynamical systems that are completely different from each other and mixing, right? Non-mixing, excuse me, orbits don't mix. That's what it means to be totally invariant. So on the one hand, we have the Fatu set. The Fatu set is a normal, so it's the open set where the family of iterates looked as a sequence of functions or a family of functions is normal. You can think of equicontinuous if you prefer. On each of the Fatu components, you have normality, and therefore you have limit functions, etc., etc. You could look at it as the set of initial conditions where every orbit behaves similarly to what the neighboring orbits do, right? And then the complement, the Julia set. So the Julia set is precisely the boundary between these different Fatu components or these different open sets where stability happens, right? So because it's the boundary and because it supports the tension of both sides, right? So on the one hand, maybe these orbits are converging to an attracting fixed point, and on the other hand, maybe these others are doing something else. Points on the boundary there is a lot of expansivity on this boundary. This is the Julia set, and it's where all the chaos occurs. So the closure of the set of repelling periodic points is actually the Julia set, also boundary between different stable domains, etc., etc., etc. So you could characterize it in many different ways. Let me show you two examples, randomly picked actually. So if you have a polynomial, for example, all these red points are orbits that scape to infinity uniformly, locally uniformly, so uniformly on compact subsets. The yellow one, so here there is a fixed point, and this is an elliptic map. So orbits here go around, comes here, then here, etc. They eventually map to this, what's called a Siegel disk or a rotation domain. And the black is the boundary in between these two things. And that's where super expansivity occurs. So if I take a neighborhood of these black points, actually, when you start iterating, it will end up filling up the whole plane. That's Montel's theorem, etc., etc. But I also wanted to show you a transcendental one. What does transcendental mean? Transcendental means that infinity is an essential singularity, okay, as opposed to rational maps, where infinity is just a regular point. So infinity is an essential singularity. The map does not extend to infinity. So this is an example just to show you that the Julia set can look very different. Here it's compact. Here it's like a Cantor set of curves. White is in the stable set. Gray is in the stable set. Just so you see that they look very different, right? Although they share many, many properties. So the Julia set, as I said, it's closed, non-empty, self-similar, etc., etc. You could fill up a course here. You could speak for hours on the properties of the Julia set. Basically, everything related to chaos. And there are examples of Julia sets, however, of many varied properties. Like there are connected Julia sets, disconnected, totally disconnected Cantor sets, locally connected, non-locally connected, positive Lebesgue measure. No interior, however. The Julia set either has no interior or it's everything. Measure zero, Hausdorff dimension, whatever you choose. Smooth, like for example, the Julia set of Z square, it's smooth. Julia sets that are homeomorphic to indecomposable continua for those topologies that like these objects, right? Sierpinski carpets, Cantor bouquets. So you name it. In fact, it's like all these sets that topologists had imagined in their minds, like very strange or, how would I say, anomalous objects, they just appear naturally in holomorphic dynamics. Okay, so Cantor sets of curves, there you go. This is a Julia set. Sierpinski carpets. Here you have it, right? So there is plenty of topology to be enjoyed when you iterate holomorphic functions. What I am interested in this talk, because I don't want to make here a treatise of the basics of holomorphic dynamics, it's I chose a thread that maybe doesn't need too many preliminaries and that can connect quickly with other things that are more basic knowledge, right? Basic, I mean, considered in the regular curriculum. And this will be the analysis on Fatu components. So I'm going to look precisely on what these components of the stable set look like dynamically and their boundaries. So a little bit of the stable one, a little bit of the Julia set. So let me observe that the Fatu set, the stable set, is open. So since it's open, and typically, not always, but typically, it consists of infinitely many components, right? Like we saw in these pictures. So, which may be simply connected or not. They may have holes and millions of things. We will today concentrate on simply connected ones, but these are called Fatu components. So the different connected components are called Fatu components, and their boundary, remember that the boundary is in the Julia set. So when one component maps to another, it does it in a, I will not say proper, because maybe the degree is infinite. You could have unbounded components, right, that map to unbounded components with infinite degree, or to bounded ones with like a covering. But the thing is that the boundary maps to the boundary. So somehow what you get is kind of a dynamical system on the set of components, right? So you can look at the components as elements of your system, and then it is obvious that has only three possibilities, right? When you take a component of the Fatu set, either it's periodic, so after a certain number of iterates, it comes back to itself, or it's pre-periodic, so it iterates for a while and then falls into a cycle, or it's neither of the two. So this is not a theorem, this is obvious, right? So, or it's neither of the two, which means that it iterates, right? And its orbit never intersects any of its backward or forward iterates, right? So that's what's called a wandering component. So, because I repeat, it's important to understand that components map to full components, okay? So it cannot happen that a component of the Fatu set maps to a piece of another one. So they map one to the other disjointly. Okay, or unless it's invariant, of course. Okay, so as I said, we have these three types of components. Now, it turns out that the pre-periodic ones are like boring because they inherit whatever you know about the cycles of components. So if you have a pre-periodic one, there is not much to say, although you could say things, but we will concentrate on periodic components and wandering components. Okay, so let's start with periodic Fatu components, and let's see immediately or very quickly what the relation to inner functions or to bounded analytic maps of the unit disk, some object in analysis, what the relation is. So we will only talk about simply connected components because since I chose to stay in entire functions, most of the time this is what we have, and this is just to simplify the discussion. If not, you need to consider other relations. But today we will just think of simply connected components, which in a very wide class of maps, these are all there are. So if you have a simply connected component, we all know that there is a conformal map, a Riemann map, that maps the unit disk conformally onto the simply connected set, right? So using this Riemann map, which by the way, there is a little bit of choice on those maps, as you know, but using any of those Riemann maps, we can build this diagram. So we can conjugate, so we can consider the Riemann map that sends D to U, and then construct this map G, which consists on following this diagram like this. So phi minus 1 F phi. And this is then a holomorphic map of the unit disk into itself. So any such map has radial limits existing almost anywhere. And as long as one can show that actually it's really an inner function, which just means that almost all these radial limits are on the boundary of the disk. Okay, so this is a special type of holomorphic maps of the disk, which is very general, and that's the one that usually one studies. Careful, very careful, because neither G nor phi extend continuously to the boundary of the disk always. So it may do that, but in general, it doesn't. So the Riemann map, because it's conformal, remember, it's bijective, extends continuously even only if, and here is the first connection to topology, the boundary of U is locally connected. Remember what a locally connected means? So locally connected, a set is locally connected if for every point that I take and for every sufficiently small neighborhood U of Z, when I look at U intersection the set, I get a connected set. So the typical non-locally connected set is the comp, right? That's the most famous example. So if I keep putting arms like this at half the distance to the end, oops, sorry, I can't, okay. But you can all see probably that if I take a point here and I look at the neighborhood, no matter how small I do it, the intersection will be disconnected because these arms accumulate on this side here. So this is the first topological connection. So the boundary of U needs to be locally connected. This is the famous Kara-Theodori theorem. Okay. G, in fact, is different because this is not conformal. This has the degree that F has on U, could have finite degree or infinite degree. And G extends holomorphically actually to the boundary if, for example, so it may have other reasons, but for example, if the degree is finite, then this is a finite Blaschke product, and by Schwarz reflection, it just extends to the whole sphere, actually. Okay, but if the degree is infinite, then it cannot extend to the whole boundary. It always has one point, which is a singularity somehow. Well, it turns out that the interplay between the Riemann map and this inner function associated here really makes beautiful mathematics and allows you to say a lot of things about your dynamical plane. This is the dynamical plane level and around what's going on your Fatu component. So let's look at some example. And this is the very well-known and celebrated Denjoy-Wolf's theorem, but which is a very surprising theorem if you ask me, and very powerful. It already started in 1880 with the lemma of Schwarz, and it's kind of a refinement of that. But it was actually proven on 1926 independently by Denjoy and Wolf, actually retroactively somehow. One gave a proof, the other made it better, the other also made it better, and this was like in a matter of months. And finally they gave the theorem both names because both had very much work on it. So if you have a function from the disk to the disk and it's holomorphic, no other hypothesis. Either you are in a very easy case and you are in a Mobius transformation. In fact, in an elliptic Mobius transformation, this one that is a rotation with respect to the Poincare distance about some fixed point, right? So this one. Or there exists a point maybe inside, maybe on the boundary, and every orbit on the disk, when you iterate, converges to this point. And that's it. There are no more options. Never two fixed points. And so either everybody goes around a fixed point forever, or they all converge to some unique fixed point, which may be inside, or may happen to be in the boundary, and who knows, I will not say fixed point in that case, because G it might not be defined on any point on its boundary, okay? But anyway, all these iterates converge to this boundary point. Okay, so this is at the level of the functions of the unit disk. Now, can we transfer this? Can we take in this diagram, this is what we know down here. How do we transfer it up? Well, it turns out that in the case that the fixed point is inside, it's very easy to transfer it because this is a conjugacy. This diagram commutes inside, right, in the interior. So that will, as we will see, transfer easily. But the real interesting question is, what about if the Denjoy-Wolf point, as it's called, is on the boundary? How do we transfer the results to the dynamical plane? So this is not simple, this is delicate, right? Because what happens if the boundary of U is not locally connected, maybe in any point? So who is the right candidate for phi of P, right? Maybe there is not one point that is the candidate for phi of P. And well, how do we know that? Because there's such high discontinuity of this Riemann map on the boundary, how do we know what happens upstairs, right? It might very well break. But it turns out that no, that one can actually overcome all these difficulties. First, let me show you, and this will be the only proof I will do in this talk. Let me show you that every point up there needs to converge to the boundary, and then we will show that it actually converges to one particular point. But first to the boundary. To the boundary is very easy because you only need to show that it exits every compact set. Right? So you can kind of exhaust your set by compacts. And if you show that a point on a compact set always leaves it and never comes again, you are done. And this is kind of easy because if Z is in this compact set, then phi minus 1 of Z is also in a compact set, which is this phi minus 1 of K. We can use this back and forth as long as we don't touch the boundary. And since we are downstairs, this omega, which is this this image here, we know that Gn of omega converges to the P boundary point. So Gn of omega is not in this phi minus 1 of K compact set for every large n, and this transfers up, right? So the conjugacy tells you that f to the n of z is not in your compact set for every n large. And you do this for every point, for every compact set, etc., and you are done that every orbit needs to approach the boundary as I iterate. So how do we make it to say, we want to say that it actually approached one particular point on the boundary. And for that, we need to use some other magic tool, which is Schwarzschild lemma, also a classic, which says, if you look at the hyperbolic distance instead of the regular Euclidean distance, which hyperbolic distance in U just means transporting the Poincare metric up, right? It turns out that every holomorphic map in between reasonable sets is a contraction on the hyperbolic distance. So if I look at the hyperbolic distance between images, it's always less or equal than the hyperbolic distance between points. This is really a magic tool that solves many problems in holomorphic dynamics. Equality only occurs when H is an isometry, an isometry as a map, so that this is strictly less for everybody or equal for everybody, so it cannot mix. And using this tool, you can actually show that it needs to converge to one particular point, no matter if it's in the very ugly set, I don't know. And here I will not give many details, but let me say that we do it using Schwarzschild, okay? So basically, we will take a point, we will take its image, right? And then because the hyperbolic distance has to decrease, okay, so since the hyperbolic distance has to decrease, if this distance between W and f of W, whatever, is less than a certain R will be any the number that corresponds, this has to be true for for all the iterates, so the hyperbolic distance between Fn of W and Fn plus 1 of W needs to still be less than R for every n. But since, but this what tells you is that the actual Euclidean distance, because we know that this is tending to the boundary, and remember the hyperbolic distance is basically like 1 over the distance to the boundary, more or less, right? So because we know that this is tending to the boundary, the Euclidean distance between these points must be tending to 0. Okay, and with this you can already show that any accumulation point of this sequence of points which lies in a compact set of the sphere, so these accumulation points exist, you can see that any accumulation point, let's say Q, needs to be a fixed point. So it needs to be either a fixed point of the map if F is continuous at this point, or it needs to be infinity, and infinity an essential singularity. So the only point where maybe F is not continuous at is infinity if it's an essential singularity. And fixed points are a discrete set. So this is discrete set, and the accumulation set is a continuum. So this really tells you that necessarily the whole sequence is actually converging to a certain point. And you could even work harder to see that the derivative of the map at this point needs to be 1. Okay, so basically, just this Schwarz peak and a little mingling with it just tells you that any orbit is converging to 1 point, and all of them to the same point, again, by this decreasing of the hyperbolic distance between orbits. So either it tends to infinity, either they all go to infinity, or they go to some finite boundary point, which happens to be a fixed point of derivative 1. So with some more work, right, and also taking care of all the cases that I left out, etc., Fatu already came up with this classification theorem. So it just said, well, just by looking at this finite number of possibilities, Fatu components, let's say period 1, because if it's period k, we just consider f to the k, these Fatu components can only be basins of attraction. This would be everybody converging everybody converging to a fixed point inside the Fatu component. So it's the Denjoy-Wolff point in the inside. Or parabolic basins, which means the Denjoy-Wolff point is on the boundary and everybody converges to this boundary fixed point, right? Or it's a Baker domain, as it was called, which means every orbit converges to infinity, which is an essential singularity. Here you have an example. Or it's the elliptic case, which could also happen, right? So a fixed point and everybody goes around this fixed point like an irrational rotation. And that's it. These are the 4 possibilities for an entire function in the dynamical plane. So this is a success story, right? Already 1920, 1926, this was Denjoy-Wolff at the same time as Fatu, and they came up with this full classification of the dynamics inside a periodic component. This makes it all more surprising that if you ask such a natural question like, what happens on the boundary? So does this tell me what's going on the boundary of these Fatu components? Well, it turns out that almost 100 years later than Fatu's classification theorem, this is not completely solved yet, okay? Even if we understand completely the dynamics of the inner function, so on the disk, on the boundary of the disk, which is not always the case, but even if we understand them perfectly, can we really transfer these results up to the boundary of the Fatu component, right? So here in this diagram, it's not obvious that knowing what happens on this boundary, if this map is really discontinuous, what can we say about the dynamics on the boundary of U? Well, it's true that radial limits of the Riemann map exist almost everywhere. This is a theorem. So using these radial limits, you kind of can speak about a boundary map. So you could say, well, I defined a map to each point, I assign its radial limit, and this will be defined almost everywhere on the boundary of the disk. Indeed, the diagram then will still commute somehow, but it will commute once. It's like this map, this boundary map may be so discontinuous that the asymptotic dynamics of the inner function maybe do not correspond to the asymptotic dynamics on the boundary of U. Okay? So this question of whether they do or they don't, and under which conditions they do, and are there examples where they don't, this is motivated a lot of work, and we could start analyzing components one by one, but this would take us more time than the one I have. So let me just concentrate on one type of components where I've made contributions so that I know better what I'm talking about somehow. Right? So we shall comment on this also because it's more recent. So for Baker domains, okay? Let's just look at Baker domains. Here is an example. This is the map Z plus 1 plus e to the minus z. So all of us, in 1 second, we can see that there is a Baker domain here, because if the real part of Z is large, then e to the minus large is really small. So this map is really Z plus 1. So this is Z plus 1 as long as I'm a little further to the right, okay, more or less. So every point here moves like a translation by 1 towards infinity, which is an essential singularity because there is an exponential. In this example, the degree is infinite, because here there are plenty of zeros of the derivative. They are all here. So you get the infinite degree. And the associated inner function has obviously the Denjoy point at the boundary. I mean, this is obvious because every point is converging to the boundary. So it's one of these cases that we were talking about, where P corresponds to infinity, the essential singularity. Okay? So it turns out that the answer for Baker domains is not, oh yes, we can always transfer, or oh, we know perfectly what happens on the boundary. No, this is like a zoo almost, okay? So let me say, what would be the question here? Well, if every point on the, on this half plane is tending to infinity, it's a fair question to say, what about the boundary points? Do they accompany these points towards infinity? And the answer is, well, not necessarily, of course not. Actually, the answer is for sure not, because where are the periodic points? Like this map has a Julia set, which has a dense set of repelling periodic points, and those points are not tending to infinity. They are on the boundary of this component, right? So clearly not every point on the boundary will tend to infinity. How many of them do? Are they all maybe with bounded orbit? So these are the type of questions that one may ask. And to answer that, you need to kind of classify Baker domains, because depending on which type of Baker domain, the answer will be one or another. And the classification is, again, relatively simple, because it is a classification based, again, on the inner function that we associate to. So we have seen that every map with a Baker domain associates to one of these inner functions with a Denjoy-Wolf point on the boundary. So Cohen in 1981 gave a beautiful classification of these maps, no matter how complicated they are. And he said, well, it turns out that every one of these has kind of an absorbing domain, like a little part, usually it's a horocycle, right, around here. Every orbit ends up there, and on that absorbing set, the map is conjugate to a Mobius transformation, a simple one. Either A times W in the half plane, okay, so something like this, the dynamics go hyperbolically like this, or the half plane should be like this, because this is W plus, excuse me. Okay, I start over. So either A times W like this, or Z plus minus I, so every orbit converges to infinity parallel to the boundary, or Z plus 1 on the plane, which means this doubly parabolic type. When we look in the disk, actually, this means either I'm converging kind of geometrically towards the Denjoy-Wolf point, or I'm converging tangent to the boundary. I exit, so I have a repelling direction like this and an attracting direction on the bottom. Or I have the attraction, the attracting direction is straight, and the repelling directions are tangent, so that I go tangent to the boundary and converge tangent to the radial line. Okay, so these are the only three possibilities that I have for such an inner function. Well, if my Baker domain via the Riemann map connects here, I will call it hyperbolic type. If it connects here, I will call it simply parabolic. If it connects here, I will call it doubly parabolic. And it turns out that many years later, 98, okay, so 10 years later, no, actually much more, sorry, 20 years later, well, sorry, it depends, 10 and 20. So during Magnier, and then later Koenig, but really during Magnier made a fantastic paper describing what the dynamics on the boundary for these three types of maps are in terms of ergodic theory somehow. So here, for example, they said, well, if I am here, even if this map is really bad on the boundary, but it will be true that every orbit on the boundary, almost every orbit on the boundary, will also converge to this point. Same here. Almost every orbit in the boundary will converge to the Denjoy-Wolf point. Instead, here it's a 0-1 theorem, because here almost nobody on the boundary in the in terms of Lebesgue measure will converge to the fixed point of Denjoy-Wolf. So this is every point, almost every point, excuse me, is topologically recurrent, which means that it goes wherever, but it visits a neighborhood of itself. Its orbit visits a neighborhood of itself infinitely many times, and therefore it does not converge to P. So there we go. We have this classification at the disk level, right? Hyperbolic, simply parabolic, this makes one class in terms of dynamics on the boundary, and then doubly parabolic, which makes the opposite class in terms of dynamics on the boundary. And the question is, can we transfer this to the boundary of the Baker domain? So when we are on the boundary, do points escape, do not escape? Observe that converging to the Denjoy-Wolf point on the disk is like asking whether orbits escape to infinity on the boundary of the Baker domain. Well, so a very recent contribution. So here there were some partial results for some time, and in 2019 with Baransky and Harke and Karpinska, we could prove the following theorem. It doesn't finish the problem, but it really advances it quite a bit. And I have to say also that it's based on previous work, or inspired by previous work of Stallard and Ripon. So we need the follow here. It's nice to see what the next ingredient is. So even if the problem in order to lift or to transfer the results is local connectivity of U, right? It turns out that the hypothesis you need to ask in order to overcome this difficulty has to do with the inner function. So the hypothesis is, if the inner function extends holomorphically to a neighborhood of the Denjoy-Wolf point, so in other words, if the Denjoy-Wolf point P is not a singularity of the inner function, so that it actually extends holomorphically to a neighborhood, then we could summarize the theorem saying the results transfer. So if the Baker domain is hyperbolic or simply parabolic, almost every point will escape to infinity on the boundary. And in the other case, if it's doubly parabolic, almost every point will stay recurrent, so it will not escape. And this is all in terms, of course, of the harmonic measure, because the harmonic measure is really the transport of the Lebesgue measure on the boundary of the unit disk to the boundary of your set. So you see, as long as this is not a singular point, as long as G is nice in a neighborhood of the Denjoy-Wolf point, then all the results transfer well. And well, so let me just give you an example before continuing, saying, so look at this, right? So this is Z plus e to the minus Z. We can check, even if the distance between these points is tending to 0, this is slowly, also all points are slowly marching up to infinity, right? Sorry. Ah, I cannot see it, it doesn't matter. So, okay. So all these points are marching towards infinity. You have many Baker domains. And it turns out that in this example, because it's doubly parabolic, the set of escaping points on the boundary has harmonic measure 0. So basically everybody, even if everybody inside tends to infinity, basically nobody in the boundary or nobody visible tends to infinity with the interior points, okay? Well, there are several conjectures about this particular map, right? Like, I think that basically every escaping point is not accessible from the inside even. So they are really hidden. So this hypothesis of niceness or regularity of the Denjoy-Wolf point cannot be removed, because already Dering and Magnier and Aronson in 78 actually gave an example of a simply connected Baker domain, infinite degree, doubly parabolic, so all the ingredient, but everybody, almost everybody escapes on the boundary. So this is an example of not transferring. So dynamics of the inner function do not always transfer to results of the function on the boundary. Okay, so this finishes everything I wanted to say on Baker domains, and now I will just make some final remarks on the other type of stable components, because this, what I'm going to talk about now, is work in progress. So let's just go back and recall where this came from. It came from the three possibilities we had for Fatu components. Remember, we said either they are periodic, pre-periodic, like the boring ones, or wandering. Periodic ones, we have kind of talked about them. Inside, everything is known. On the boundary, not everything is known, but, well, some work has been done, right? What about wandering? And here is like más difícil todavía. So wandering domains, can inner functions help us also on talking about wandering domains? Right? So wandering domains, again, can only exist for transcendental maps. In fact, not even for every transcendental map, but we'll leave this for another day. So it's a wandering domain, as I said, if the intersection of the iterates is always empty. Here is an example of a wandering domain, right? These black blobs map one to the other, z plus 2 pi plus sine z. This is a wandering domain that escapes to infinity. And wandering domains is quite an uncharted territory. If Baker domains are already kind of rare, I would say, rare not in the sense of probability, yeah? Rare, I mean that there's not so many people experts on Baker domains, even less for wandering domains, basically because they do not exist for rational maps. This is a celebrated theorem of Sullivan, because they are kind of recently discovered. Until the 80s, nobody knew if they even existed. Also because it's very hard to construct examples. So wandering domains are not associated to any periodic orbit. So it's not so easy to construct examples of them. That's why they didn't find them until the 80s. And because also not every map can have a wandering domain. So the simplest maps, that it's the ones that mathematicians look at to start somewhere and to build a theory, those ones don't show wandering domains. So they are not in the mainstream, or they have not been in the mainstream, because right now, I think the most challenging questions that are in the field of transcendental dynamics are about wandering domains. So let me just very quickly tell you about the easiest way to construct wandering domains. And this is by lifting periodic components. What do I mean? Let me give you an example. So imagine that I have a function on the plane -1 point, almost somehow, well, meaning that this point 0 is, it only has itself as an image or pre-image. Like, for example, this one, lambda w squared e to the minus w. It's not important, the formula, it's just to show you that this exists. And now suppose I make a change of variables of the logarithm. So I just make this diagram commute. You can check that this diagram commutes, and that, so going by log lambda, which is a constant, plus 2z plus minus e to the z, and then exponential is equivalent to going this way. So this is what's called a semi-conjugacy. And it turns out that this map has 0 as a fixed point. You can check that, it's easy to see. And in fact, as a super attracting fixed point, meaning that 0 is a 0 of the derivative too. So when I lift it by the exponential, what I get is basically a left half plane. And if things converge here, because this is attracting, orbits here will converge to -infinity, which is where e to the z sends it to 0, right? So this is a Baker domain. But now it turns out that there's other possibilities here. I'll show you pictures in a minute. For example, if this has another attracting basin attached here, as it happens for certain values of the parameter, when I lift this by the exponential, I will get like infinitely many copies, of this domain. And because of this conjugacy here, maybe one will be fixed, but the others will just map, because this map is basically 2z, up or down, building a wandering domain, or actually infinitely many orbits of wandering domains. Okay, so let me show you this. Here is what I was describing to you. So in this case, this is exactly what I was describing to you. This is a Baker domain. And these are the lifts of the basins I told you about. So this one is fixed, but all the yellow ones, they just map up or down, right? And build wandering domains. And in the same way that we've done this with an attracting basin, by playing with a parameter, you can do this, you can have this to be parabolic, for example. So if you take another parameter value chosen, you will have that this is a parabolic basin. So every orbit converges to the point on the boundary. And the others are wandering domains going up or down. But, let me give you a third example. So here, here I show you the map downstairs and the lift. Here, this white tiny region is the basin of 0. And this gray region is the Siegel disk that is attached to it. Right, this rotation domain. So when you lift, you get the Baker domain here, and here are the copies of the Siegel disk, which wander around. So let me just point out that orbits remember where they came from. So this is another example, right? For example, it's true that every component maps to the next, but it's not a translation. There's a fixed, what it was a fixed point, now it's like an orbit that these ones do translate, but all the others, like this one at the next iterate is closer and closer and closer. So by lifting, orbits remember where they came from. If they came from a basin of attraction, orbits will converge to the orbit of the old, of the former fixed point. If they come from a parabolic basin, orbits will converge to the orbit of the parabolic fixed point, etc. If they come from a rotation domain, they will kind of keep rotating, even if the thing is moving away, right? It's like if you are in a ship. So a question, how special are these examples as wandering domains? Can other internal dynamics occur? So can we actually look at where I'm aiming? I'm aiming at a classification theorem like the one that Fatu made, right? Can we say something of what's going on inside the wandering domains in the same way that we did with periodic components? a priori, this is much harder because there is no iteration to be talking about. So there's just, every domain is different. So there's no relation a priori between one domain and the next. This is kind of non-autonomous dynamics, right? So, well, on multiply connected wandering domains, there was some success, so maybe yes. Actually, let me just make a 1 second interruption to say that from this point on, this is all joint work with this fantastic group of people like Ripon, Stallard, Anna Benini from University of Parma, and Vasiliki and myself. And let's look if there is another relation with inner functions, because it worked so well the last time, right? But what happens here? Well, it turns out that U is different from the image and it's different from the next. So every wandering domain, every piece of it, it's different. So I need different Riemann maps. Everyone will come with its own Riemann map. There are several choices, but basically, if I try to build the same diagram, I do not get a conjugacy. I do not get one inner function. I get infinitely many inner functions. So these are all inner functions, and I can look at these forward dynamics, right? So I could look at G1, G2, G3, which consists, Gn consists on concatenating from G1, little g1 to little gn. This is still an inner function on the disk, but this is a non-autonomous dynamical system. This is not iteration. So no Denjoy-Wolf, no theory, no Dering-Magne, nothing in the classics talking about this. And in the modern, not so much. So many people has worked on sequences of analytic maps on the unit disk. Filippo, for example, has done beautiful work on that. Madrigal, Contreras, many people. I mean, I could mention a lot of them. But there are so many aspects to look in non-autonomous dynamics on the disk that rarely you find exactly what fits your questions, right? So let me say that to answer the questions that we have, you kind of have to develop the theory from the start. So again, Schweitz-Pick comes in very handy. This is just a review. So still from one domain to the next, the hyperbolic distance has to be decreasing. So when you look at the sequence so you pick 2 points and you look at the hyperbolic distance between them and then their images and then their images and then their images, and this is a decreasing real sequence, so clearly it has a limit, right? The question is whether this limit can be different for different points or not. And it turns out that looking in terms of this, there is some classification. So we can divide the wandering domains into contracting wandering domains. So when every pair has hyperbolic distance tending to 0, this is called hyperbolic step 0. Or maybe this decreasing sequence converges, but not to 0, just to some positive number, or it's eventually isometric and it stops decreasing. And the theorem, what it says, and this is by this group of people that I told you, the theorem, what it tells you is that this happens either for every pair of points or for no pair of points. So that this condition has to happen for every single pair of orbits, so that the domain can be classified into contracting, semi-contracting, or eventually isometric. And in the contracting case, you could even refine it into depending on the rate of convergence to 0. And I will not get into this because this is not the goal of my talk, but I wanted to tell you that this classification is possible in these terms, which is like all orbits clustered together or no, or all orbits like go around Siegel point somehow like before. But also we can talk about convergence to the boundary. So it's like a second dimension on this classification. It turns out that you can wonder whether they converge to the boundary or not. And the time is finishing, so I will just say that yes, you can also classify in those terms. So either every orbit is converging to the boundary, or every orbit is bounded away from the boundary for all times, or every orbit oscillates towards and away from the boundary at all times, okay? So this two-dimensional classification, let me put it here. I'll do it here. This two-dimensional classification fits the lifts that we did. Okay, so if I'm contracting, obviously, sorry, if I'm an attracting basin, I form an attracting basin, then I'm contracting and my orbits stay away from the boundary, etc., etc. If I'm a single disk, if I was a single disk, then I'm eventually isometric and I'm staying away from the boundary, etc., etc. But what about all the new cases, the ones that cannot be coming from lifting any periodic component? The answer is yes, they can all be realized. Okay, and I will not extend on this, but I will mention that, you know, we have talked about converging to the boundary, but do we actually converge to one point in the boundary? Is there a Denjoy-Wolff theorem for this kind of maps? And well, in general, there is not. Okay, and this is work in progress. We are working about this. We are thinking about how the dynamics on the boundary look like, but we first need results for non-autonomous maps of the disk, and then we will need to transfer them to the dynamical plane. So we do have some partial results here that may be of interest to other areas too, but the transferring to the dynamical plane level is highly non-trivial. I mean, you really need to ask some uniformity on the Riemann maps that you are using, because here you have an infinite sequence of Riemann maps that could be degenerating, and you have to have this under control if you want to have the chance of lifting some of the results that you can obtain on the disk level. And that's it. Further questions, I mean, the way we construct these examples, they do not tell us anything about the map. Can we find other ways to construct them so that we have information about which maps are we talking about? Or can we relate it to the singularities of the inverse of the map? So there is plenty of work to be done related to wandering domains and the dynamics inside and on the boundary of these Fatu components. And I think I will finish here. Thank you very much for your attention.
So thank you very much, Nuria. It was really a great talk. So buonissima charla. And
thank you.
Okay, now we need some second because in YouTube there is a small delay. So if someone wants to make a question for Nuria. Okay, so maybe when we wait, let me see. Maybe I'm... Okay, then maybe I can ask you, I have two curiosities, in fact. The first one is in your 2019 theorem with Baranski, Harke, and Karpinska. So you mentioned that this hypothesis of holomorphic extension to the point for G is necessary for the theorem, but do you have any kind of intrinsic property which allow you to get the same kind of escaping?
Yes, so I didn't mention it. Let me see if I find that. Well, it's not very necessary, but I didn't mention it, but this, because it was not a matter of giving all the details, but it is true that you can overcome this difficulty. So you could say, well, now imagine that that you don't have this extension to the Denjoy-Wolff point, right? So that in fact, this is a singularity, okay? And your inner function cannot extend. Then is it always unknown what's going on? Or is it always that precisely as in this example, is it true that every point in the boundary escapes and it's always opposite to what happens here? And the answer is no. It depends on the rate of convergence. Mm-hmm. So if you can, there is something you can say about if you converge fast enough to this point, then you can overcome this difficulty and still transfer your result and say that almost every point stays
so it's
away.
Essentially the limit of the distance from an orbit to the next one.
Exactly. It's like how exactly. So how these two points compare to each other. Okay, so in this case, the hyperbolic distance between these 2 points tends to 0. So when you are in the doubly parabolic case, this is always this step 0. Okay, but this convergence to 0 can be faster or slower. And if you ask that it's fast enough, right, then you can recuperate the result. So in this example, the convergence was very slow. Okay, so for example, actually, let me say that in this Fatu example that I put here,
so in your holomorphic condition forces this this kind of rate, fast rate.
Yes.
Okay.
Exactly. No, so you may have a singularity, but still, if you can say something about how fast I'm getting here, then this forces things to happen in a neighborhood. And then you can transfer them kind of to the rest of the...
Okay.
So this is intrinsic. I understand this is what you were asking.
Yeah, that was exactly what I...
Okay. I mean, I can give you the details, because we have also some examples, because we put some condition, which is not very... I'm not saying the details because it's not exactly like converging geometrically, or no, it's a bit more delicate. And then we asked ourselves, like, is there any example of this? I mean, can this... And yes, there is a whole family of examples that satisfy the condition that we came up with. But still there is this whole, that's not sharp. So it's not clear to me if there are other weaker conditions that imply the same.
Thank you. Okay, there are no other questions, so maybe I ask a second quick question. So in the last one, you discussing about wandering domains, and then in particular non-autonomous maps. Probably you know there are some results of Beardon and Minda and Gu and so on. So this the ZW that you find there, is it related somehow to what probably they call some kind of intrinsic block radius or whatever? I mean, so they measure they have this non-autonomous system, they look to the image, and then they measure the biggest hyperbolic distance you can put there, or so on.
Okay, so I don't know if I will answer your question totally precisely, because at this moment I don't have all these results you are talking about in my head, but sorry, I was looking for the picture. But I can tell you that here. But one of the things, now we are looking at these boundary dynamics, and one of the things that it comes up, so one of the probable conditions that we will need to ask is that there is a definite disk contained into each of these domains, right? And we are still wondering, and not only that, probably we will need like local connectivity or uniform local connectivity or something. I mean, we are still in very initial state of these, but clearly what you say is related to this. These things cannot deform too much if we want to say something when we go up, okay? So this, when we look, for example, at the image of 0, so we need to know that a neighborhood of 0 will map to kind of it will not, so that there will be no pinching. Like imagine if this was pinching more and more and more, and precisely the image of 0 was in these little pieces, right? So it's basically the derivatives of these maps at 0. How do they behave in order to know the geometric, but we would like to give geometric conditions on the top. Just geometric, intrinsic things, right? Not conditions based on this, but conditions based on here, something that is checkable even, or something, right? But yes, this definite disk inside will be necessary. So here I think the embedding of these wandering domains on the plane will be important, needs to be important, or at least we don't know how to do it without for now. So this, I think the story of the periodic components is really successful in the sense that you can do so much, even if the domains are awful, right? It's like it looks impossible, and then for some reason you overcome all these highly discontinuous and horrible prime ends and horrible topology, and you get it, right? I'm not sure this will be so nice in the case of wandering domains. So I think these two classification theorems are in the right direction. I mean, this is nice. Here you don't care so much in the classification, in these this classification that I mentioned. But when you are talking about boundary dynamics, I think there will be no way to do it without.
Okay,
thank
you very
much.
much.
Closely to what you told me and see what you meant exactly. Okay, well, thank you.
Thank you very much. So Filippo? It seems, yes?
I'm Claudio.
Claudio.
I have a curiosity. I am not an expert of these fascinating theories, but what is the role of numerical computations in guessing or disproving some conjecture? I saw that you showed beautiful pictures, and I know that it's not so trivial to get such pictures. So I think that there is also some support, right, from computational mathematics.
So, okay. Your first question, the role of the numerical simulations, or let's say these pictures that you see, is crucial. So I think in the 1900s, Julian Fatu did an amazing amount of work without a computer. Okay, so I think this is remarkable. It's like they got very far without being able to see one simple Julia set in their lives, right? But if you look at there's a beautiful history book on this by Dan Alexander, I think. And Julia drew in one of his papers, he tried to draw a Julia set, right? With little triangles and he said, well, this looks really complicated, right? And of course, if he had ever seen what a Julia set looked like, right, he would have seen that he was totally right, that this was. So I think the field was dormant. They did, I think, as much as one could do without any intuition or graphical intuition. And in the 80s, the reason why this woke up in such a way is because the computers were invented and suddenly people could see these things. And as you said, Claudio, disproving conjectures or trying to find examples, etc. Doing pictures is crucial. Now your second question. These pictures I showed, there are some that are trivial to make and some that are very complicated to make. So as usual, every time that we talk about parabolic dynamics, which are actually unstable, because if you have something with derivative 1 and you move a little bit, you are gone from the 1, right? And also because they take long terms of computation, those are not easy pictures to make. And yes, numerical algorithms play a role, and you need to know a little bit of the mathematics behind in order to make good pictures. Some others, like drawing the Julia set of z² - 1, those are basically so hyperbolic dynamics somehow, right? Attracting basing, attracting behavior. These are very simple to make, and you can give them to your students as an exercise. In fact, to your high school student, right? So some pictures are simple, and some others require some techniques, and some others. I mean, you need to have experts doing them, like. I could mention many that are real experts on doing very difficult pictures. And some of them are impossible, like a Kramer point, a point where you don't have linearization. Nobody has ever seen one because the computer cannot draw it.
Yeah. Thank you. Okay. Thank you very much.
So there is just, I think, the last question by Tommaso Pacini, and I think the answer may be quite fast. How well developed is the analogous theory on Riemann surfaces?
Well, I mean, if you analyze dynamics on Riemann surfaces, you end up thinking. So, okay, if you analyze dynamics, holomorphic dynamics on Riemann surfaces, like self maps, so that there are no points mapped to the essential singularities, then it comes up that the only interesting and non-trivial ones are like the plane -1 point, and the Riemann sphere. okay, basically using the uniformization theorem. Now, if you allow essential singularities and preimages of these essential singularities, you enter in the world of meromorphic transcendental maps, and there you have a little more to say. You can do it with one essential singularity, like the tangent map, for example, and that theory is kind of also developed, not as much as polynomials or rational maps, of course, but there is a theory somehow. But then a more general world that is coming into place these days is when you allow like a countable number of essential singularities and preimages of these, and these take place in, you could think of them in an abstract Riemann surface, why not? And this theory is very, very, very undeveloped, I would say.
Thank you. So I think, okay, it's time is over. So I thank Nuria very much again for this wonderful talk. It was really wonderful. I think I did not exaggerate when I introduced you. And so, and then I think we can resume in 15 minutes. So the next talk will be at 11:30 by Massimo Fornasier.
Thank you very much to all for listening.
Welcome back to everybody for this morning session of the Giornata INdAM Day 2020. I am Claudio Canuto. I am pleased to be the chairperson for Massimo Fornasier talk. A few words of presentation. Massimo, though I think he's very well known in the Italian community. Massimo received his doctoral degree in computational mathematics from University of Padua in 2003. Then he was a postdoc at the University of Vienna and at the University of Rome Sapienza. After that, he was a research scientist for several years at the Radon Institute, the beautiful Radon Institute of the Austrian Academy of Sciences in Linz, and including also a period as a research associate at Princeton University. And since 2011, he's a full professor in applied numerical analysis at the Technical University of Munich, TU Munich. It is worth mentioning that Massimo became already famous as a young postdoc for his original application of mathematics to the restoration of a group of frescoes by Mantegna in a Padua chapel, frescoes that were reduced in small pieces by bombing during World War II, and using original pattern recognition techniques, he was able to in some sense to solve this incredible puzzle and identify the position of the pieces based on photographs of the original fresco. So it's kind of a very, very interesting example of interaction between mathematics and art. Okay. This was somehow the start of a career that showed broad scientific interest, broad and diversified scientific interest, which is documented not only by his scientific production, his papers, but also by the titles of the courses Massimo has taught in many countries on very, very different arguments. The scientific contributions concern, among others, the application of harmonic analysis to compression, sparsity, and adaptivity in signal and image processing and in PDEs. Particularly, let me mention the generalization of wavelets to what's called the frames and their applications. Other contributions are in development of innovative minimization techniques, the analysis of analysis and control of multi-agent interactions, the study of sparse and mean field control, and more recently, the interest in data analysis and machine learning, which I guess will be the subject of his talk today. Massimo is a very versatile person. He has collaborated with very, very many people around the world. Let me just mention people like Karl-Heinz Grökenig, Hans Feitinger, Ingrid Obesci, Jose Carrillo, Peter Markovic, and among the Italians, Giuseppe Toscani, Benedetto Piccoli, Beppe Savare, just to name a few. If you look at the list of graduate students and postdocs supervised by Massimo, the list is very impressive for number and quality, and by the fact that most of them quickly got tenure tracks and permanent positions. Finally, among the recognition of the quality of his activity, I want to mention the invitation to the 7th European Congress of Mathematics and the prizes from SIMAI, the Italian Society for Industrial and Applied Mathematics, and from the Royal Academy of Belgium. So today, Massimo will speak about identification of artificial deep neural networks, which, as you know, is a hot topic nowadays, not only in academia, but also in industry and generally speaking in society. And in particular in mathematics, there are many initiatives that have been started and going on, both at the level of university departments in Italy in particular, and in the framework of the Italian Mathematical Union, and also in INdAM. So I think this talk will be particularly focused on this aspect of nowadays aspect of science. So let me thank again Massimo for being here with us today, and the microphone is to you, Massimo.
Thank you very much, Claudio, for this generous introduction, and I would like to thank all the organizers for inviting me to present in the INdAM Day. For me, it's a very moving opportunity, actually. So, may I be allowed to share my screen?
Yes.
Yes, I can. Okay, thank you. So I'll try to share my screen in its full. Okay, so today I'll present some results related to identification of the artificial deep neural networks. That is a collection of work that I did with several people, starting with Ingrid Obeschi, and then with some of my students and postdocs like Christian Fiedler, Timo Klock, Michael Rauchensteiner, and Jan Vibiral. So it happened to me some years ago to work with Jan Vibiral on a topic that turned out to have to be technically useful to attack also the problem of identification of artificial neural networks. So in a certain sense, we had the right tools and we started to work in this direction. However, deep neural networks are somehow becoming more and more known as an important tool for many applications. And however, it's not the topic that has been particularly at the attention of mathematicians. And yeah, this talk will contain quite a bit of technical aspects about the proofs and about the reasoning that we have been using for attacking the problem of identification with neural networks. But I think that it is worth that I make a small introduction that is not too detailed in technicalities about neural networks. And also I would like to spend a little bit of time in mentioning along the way some results that I consider mathematically interesting from different areas of mathematics. In fact, the neural networks are a nonlinear process. They are basically a discrete time dynamical system. And as such, as any nonlinear process, depending on the tool that you can apply to the particular problem, you may have a completely different view about the same problem. It's not like with linear problems that they can be completely understood at once with one tool, but depending on the nonlinear model that you have, you may have different tools that fits with that. And for this, I would like to touch different mathematical somehow aspects. And so, not being a mature field, I think that it is worth that I spend a bit of time on a small introduction. I hope that it is going to be appreciated. So deep learning has become a very successful approach, let me say numerical approach, that reach state-of-the-art results of various applications. Some of the most important applications are in visual analysis, in particular image recognition. So here you can see some classified images of cats and dogs, and you see that somehow these are successfully identifiable images that neural networks would identify very easily. They can be used also for speech recognition and also language translation. There are some very interesting new tools that are able to produce translations that are rather impressive. As well as we know all the stories about computers beating humans, playing, for instance, very complicated games like Go. And this is also based on deep neural networks. There are even more impressive results, like the one of neural networks interpreting text, where one describes a scene, and the neural network, by interpreting the text, is able to generate its own view about the scene described in the text. This is quite an impressive achievement, as well as achievements like the one of repainting or representing images with styles from painters, and the ability of generating corresponding paintings and things like that. So these are the kind of results that have been particularly surprising somehow many people, and attracted the attention on these tools. But what is about these neural networks and how they work? And so I think that before starting with deep neural networks and complicated nonlinear processes, I would start from the very basic, which means the neuron. The neuron is getting inputs, and depending on the inputs is firing outputs. And back to the 1969, there's been this proposal of modeling the neuron actually as a so-called ridge function. A ridge function is the composition of the scalar product of the input x with respect to a certain direction A. A is another vector. And that is maybe shifted by a shift that here is indicated with theta, and this shift is also called bias. And to the result of this linear or affine type of operation, we apply a univariate scalar function that we call g here. Now, if we, in a certain sense, integrate the bias within the nonlinear function, then we may somehow form a new function called rho, and we can describe the problem as being f equal to rho, a scalar product with x. Why this kind of neurons or somehow these units are so important, and how do they work actually? Why they are having some good effects? Well, the idea is that these functions are essentially constant in the orthogonal direction with respect to the A ridge direction. So this fact that these functions are simple because they are parameterized by a unique parameter A, and then they depend from one dimensional function, make their complexity very low. So if we think of a ridge function that maybe has value -1 and then is changing to a values 1, we can think that being constant in the orthogonal directions somehow can allow you to create a separation between two parts of the space. In this way, somehow they act as a phase field separatrix between two parts of the space. And if you sum multiple functions of this kind, What is the effect? The effect is the one of producing a tessellation, a tiling of the space. And so you can classify different elements in the space or different vectors in the space according to this, in a certain sense, non-linear and relatively smooth tessellations. In fact, there are relatively old results back to the beginning of the 90s by Chibenko and Hornik, that by using approximation theory, they proved that actually linear combinations of functions of this type are actually dense in the continuous function. So basically, you can approximate many different kinds of functions by using these building blocks. This is one of the reasons why these are fundamentally the building blocks for neural networks. Neural networks are, in a certain sense, nothing else than compositions of layers of such neurons. If you want, you can describe them as a concatenation, a composition of multiple functions, rho 1, rho L, applied to affine functions that depends maybe on a matrix W, W1, WL, and corresponding shifts tau L. These are describing how you shift the activation functions. G is our activation function here. And basically here we assume that the univariate and the scalar function G is applied component-wise to the output of these affine transformations. And so we see that these matrices may map somehow one space into the next, and they depend on somehow on certain dimensionalities. Okay. Moreover, you can consider multiple layers, and here we can have capital L layers. And as a matter of fact, the number of layers is determining the depth of such a concatenation, and the dimensions of the weight matrices. They are typically determined according to heuristic considerations. So there is not really always a theory that tells you exactly how many layers and how many neurons you may want to have, although we are recently shedding some lights about these aspects. Instead, somehow the weight matrices and the shifts, which are the parameters that are defining these neural networks, are based on a learning procedure that is based on fitting the problem to the data, fitting the parameters to the data. How does it work? So if we have training data xi, yi, let's assume that xi is an image, maybe an image of a cat or an image of a dog, and y is representing the label that is mentioning whether the image is in fact a cat or a dog. Then we try to fit the parameters w and theta by minimizing a certain discrepancy that is telling us that the neural network is supposed, given a certain input, to give the right label. Okay, to give as an output the right label, and this is by minimizing the discrepancy with respect to the input and the label output. Of course, somehow this is one way of considering the loss, and there are many other ways to do that. Maybe by using entropy or by using Wasserstein distances now become more and more popular to consider different kind of discrepancies to fit the network. So what we know already about this training phase is that whenever the number of samples or training data, n, so here we have been considering n training data, is of the order of the complexity of the network, which means that it's the order of the number of parameters of the network, then it turns out that there exist networks that would make the loss equal to 0. Which means that we are able to interpolate all the data exactly. If you want some very nice mathematically developed theory about this ability of interpolation, maybe you want to make a reading of the paper of Verschining that I indicate here. So we can imagine that the loss as typically a non-convex profile. The reason is that the neural network is highly non-linear. So even if we consider a mean square error here, it's most likely a highly non-convex type of loss. As a matter of fact, multiple networks may be optimal. And this is also due to symmetries. In a certain sense, if you permute the order of neurons within one layer, the output won't change, as well as if activation functions like the hyperbolic tangent are symmetric, then all of a sudden you can change the signs of the weights and still obtain the same output. So it's so there are one can expect then that there are multiple optimizers that minimize the loss. In the over-parameterized regime, so when the complexity of the network or the number of parameters of the network is significantly larger than the number of samples, then the loss landscape tends to become increasingly less non-convex. And this is some work done by Montanari and others and many others. So these are things that are attacked by different angles and understood in different ways. But morally, we know that more parameters you have, less non-convex is the problem. Moreover, over-parameterization is not bad in this case because despite the fact that over-parameterization would mean certainly fitting the data, this does not cause what in statistics you call overfitting, which means that you are obtaining a model that is too biased with respect to the training data, rather than being able to generalize to data that are unseen. The reason for this surprising fact that over-parameterization does not cause overfitting, it's most likely hidden in the optimization methods that are used to minimize the loss. In particular, people are using stochastic gradient descent that is performing most likely an implicit regularization that in fact is promoting low complexity networks. So there is this kind of effect of implicit regularization that allows most likely to obtain nevertheless networks that are able to generalize well. But this is partially understood, partially not understood. The research is very strongly focusing on these aspects. In support of deep learning come, of course, the empirical evidence of being able to outperform other methods. So we have seen already many of the examples of applications. And in particular, computer scientists set, in order to give scientific ground to their analysis, certain kind of certified benchmarks. So they try to overcome certain other methods or performing better than other methods or on certifiable benchmarks. And this is the way things are progressing mostly in the field of applied computer science. Nevertheless, there are, of course, theoretical discoveries that actually show that deep artificial neural networks can approximate very complicated high-dimensional functions without incurring in the curse of dimensionality. So this is really an interesting fact that is actually used, for instance, in the solution of high-dimensional partial differential equations. And it turns out that maybe using other methods like finite element methods or other more classical methods, you would crash against the curse of dimensionality. But if you use the neural networks, all of a sudden, it turns out that solutions are possible without such a problem. This is a surprising aspect of deep learning. issues of the training phase. So while the approximation properties, as I mentioned, of neural networks are becoming a little bit more understood and transparent, still this optimization, somehow this method that selects one possible optimal network, it remains a little bit a black box. So, and we still have to understand what is going on. And the reason is that due to the very large number of parameters and the potential variety of local and global optima, the result of the training is still quite difficult to explain and interpret. So this is something that is a very in the focus of the people that are, from a mathematical point of view, trying to understand what is going on there. There are recent results that are shedding some light on this important phase of the neural networks, and at least in some simple cases, the cases that have been treated in the literature are mostly linear neural networks. So when somehow the non-linearities are, and so we are basically the identity, and we are considering a sort of matrix decomposition. In this case, there is a clear understanding that gradient descent would implicitly promote low-rank solutions. And for shallow neural networks, by using mean field approximation, the people understood that gradient descent actually is minimizing a convex or tendentially a convex type of landscape. The generalization ability of neural networks trained by such methods can be challenged by adversarial attacks. What does it mean? It means that these networks have Lipschitz constants that typically are huge. It is possible to move a little bit from the given input and obtaining a completely different result. So there are some weaknesses in the deep neural networks that needs to be further understood. And last but not least, the number of parameters in the training phase needs to be very large, as well as the training samples. So if you want to really have good results, you need a very large amount of data. And on top of that, in order to make a stochastic gradient descent working, you need to have an over-parameterized network, so a very large complexity of the network. And so you need resources to get data, and you need computational power to do the training. Okay, we get to the point of identification of neural networks. Let's assume that we are now in the realizable regime. I call this realizable regime the regime where the number of parameters is scaling more or less as the number of samples. And in this case, we know that there are networks that are interpolating the data, okay? So we are in the situation of this kind. And we would like to show that in this realizable regime, generic neural networks that fit the data are essentially unique. There are not many other networks that interpolate the data up to symmetry. So that up to symmetry, the landscape that you can think is a little bit less convex, okay, but certainly it has a unique global minimizer. That's what we would like now to address. Identifiability means that there are no other networks, smaller or larger, than can really do the same task. But also robustness implies that if you have a larger network that performs a task, you can reduce it to a minimal network that potentially somehow have significantly less number of parameters that approximatively do the same task. So somehow identifiability has also this kind of implications that somehow indicate that you can overcome some of the troubles that I mentioned before, in particular explainability and uniform stability. So the unique identifiability of networks is a long story. It started more than 3 decades ago with the work of Sussman and Albertini for concerning somehow one-layer neural networks, so very simple networks. And then the ground-breaking work of Charles Pfefferman that compared to certain kind of very applied papers somehow in the field. It's a very, it's not very much cited, but it's a great piece of math. And I like to mention it because it's very beautiful result. So it says basically that a generic fully connected deep neural network with activation function equal to the hyperbolic tangent is uniquely identified by its output up to natural symmetries. This result is amazing in a certain sense because it's based on the fact that the hyperbolic tangent is a meromorphic function. So it's a holomorphic up to a countable number of poles, and it is I-periodic. So you can more or less describe these poles in a very simple way. Moreover, whenever you sum or compose dilations and shifted versions of this hyperbolic tangent, they are again meromorphic functions that have maybe multiple poles, as I illustrate here in this right figure. And the positions of these poles, of course, depends in a very clear way on the way you basically dilate and shift the hyperbolic tangent functions. Therefore, these poles are basically encoding the weights and the shifts of the network. Okay, so these are, in a certain sense, countable objects that are completely described by the architecture of the network and so on. And so, if two networks coincide on the Euclidean plane by using suitable analytic extension arguments, they must coincide everywhere on the complex plane, and in particular, they need to have the same poles. But due to the fact that they have the same poles, they need to have the same architecture. This is really a remarkable, a quite remarkable result. Okay. So there's been some generalizations of this result and so on. So, however, these are results that are based on the idea that you can really consider every possible input and output of the network, right? So you can observe everything, and by observing everything, necessarily there is only one network that does the job. But here we are somehow dealing with functions that are determined by a finite number of parameters. And despite the fact that the identification is known since the 90s to be, in general, an NP-hard problem, it is not at all expected that generically this kind of network require an infinite amount of samples to be really determined, right? So we need to understand how many samples do you really need for identification. Now, if you use stochastic gradient descent and you try to fit the network data that are realized by a network, and you try to see whether by minimizing the loss, you will be able to recover exactly this network, unfortunately, this doesn't work. So it is not happening. And you see that stochastic gradient descent basically saturate to a certain L infinity distance between the real network that you want to find and the network that somehow the stochastic gradient descent will compute. This network will fit the other network on the data exactly. It will have most likely a small L2 norm distance, but you won't have a small L infinity norm. And so we need something else, some other approach to deal with this problem. And let's try to discover this new approach by going back to the neuron again. So if you remember, we described the neuron as a ridge function with a certain raw nonlinearity and a certain parameter A. Yes, so other questions or no? Okay. Somehow the idea is to go through a linearization. So if you linearize, which means you differentiate the neuron, what happens is that the weight that is hidden inside the belly of the neuron gets exposed outside, And you can test this weight with respect to any kind of differentiation direction that you want to perform. If you have enough smoothness, you can use finite difference approximation. So you can use samples of the networks in a suitable positions. And so you can basically determine this kind of testing of the weight by using a certain direction phi. Now, by sampling uniformly at random the position where you want to differentiate and using random derivatives directions, phi k, you can basically build a linear system of the kind that you find here below, where you have multiple equations, as many as the points that you sample on the sphere, or you sample somehow on the positions where you want to perform the differentiation. And the idea is to solve stably this kind of linear system. So if you're able to solve stably these linear systems, then we will be able to basically compute the ridge direction. And then once the ridge direction is computed, then the neuron can be identified. It's not very difficult. So the algorithm works like that. We try to solve the linear system by suitable regularization. Here we use an L1 regularization because we can take advantage of some results in the field of compressed sensing. But you for every possible points on the sphere, you basically try to solve this linear system. Out of the solution of this linear system, you try to find the one that is most stable, which means the one that is the largest L2 norm. You define a possible ridge direction A hat as the normalization of the result. And then you define a new ridge direction by sampling the neuron, taking advantage of this proxy of your ridge direction A. And then finally, you have an approximate neuron. So if you use this algorithm, you can prove that under a certain assumption that depends on how the derivative of the activation function behave, using a finite number of point evaluations of the neuron, then it's possible to construct another neuron that has a very small error that depends on the finite difference step, epsilon, but also on the number of samples that we have been using, and depends on this parameter alpha that comes into the game here, that depends on this derivative of rho. But nevertheless, interestingly, we have a uniform approximation. So we have an approximation in L infinity of the neuron. And how does it work? Well, by using compressed sensing, you can prove that the results of these optimizations that we have in the first step of the algorithm will be equal to the ridge direction up to a scalar and an error that you can estimate by this gamma. And gamma is given by the theory of compressed sensing as described here. Once you have that, you can prove by algebraic computations that the normalization of x hat j is not far, it's basically up to sign equal to the ridge direction with an error that depends on gamma and inversely proportional on the norm of xj. Under the assumption about this derivative that alpha is strictly positive, it's possible to prove that there exists a xj that is actually larger than alpha to the 1 over 2. Morally, this is what happens. And because of that, then you have the result. And once you have the ridge direction, you can easily show that due to the smoothness of everything, you have also the neuron. And so it's basically the way you can proceed. Okay. So the question is how far we can bring this idea to the identification of a neural network. So I skip directly to the shallow feed-forward neural network, the networks that have one hidden layer or one layer. They are called shallow neural networks, which are basically sums of ridge functions, right? And so the idea is that how can we really identify these neural networks? In particular, how can we identify the weights AI, and how can we identify the raw I, which are representing basically the activation functions shifted and so on. Okay, how can we do that? So we start with a case where the number of neurons is less or equal than the dimension d of the input, and the AI, AM are linearly independent. Okay, we start with this case, and we proceed as we did for the neuron, and we perform a first-order differentiation of the network. Unfortunately, differently from the case of the neuron, the first-order differentiation gives us linear combinations of the weights, and therefore it gives us information about the space that I call A, which is the span of the weights, but it does not give any information about the weights itself. In order to get information about the weights, the only way is to go beyond the first-order differentiation and going into higher-order differentiation. And this leads us to essentially having tensors. Okay, so here we do have tensors, and the problem will become, so the identification of the network become basically how can we perform in a stable way tensor decomposition, a symmetric tensor decomposition into rank 1 tensors. That's more or less what one can do here. And so here, somehow, how can we approximate these gradients, or how can we produce this kind of tensors? Well, there are two ways. One way is using finite differences and approximating the strong derivative, or going into using passive sampling, which is basically exploiting weak differentiation. How that work? Let's assume that we have a density of the inputs xi. So we do have that xi are generated at random according to a probability distribution that has a certain density p. Then, by using these samples that we don't choose in the active sampling, we have to basically choose this sampling in order to perform the finite differences, right? But here it's not necessary. You can also take the samples fxi. With these samples, you construct this tensor by summing them up with respect to certain kind of higher order differentiation of the density. So for n large enough, certainly these sums are very close to this integration with respect to the probability measure. The density is simplified, but using basically a differentiation by parts. You basically move the differentiation over the network, and at that point, basically, you are back to producing a tensor of that kind. So again, somehow we are able to produce tensors, and the tensor decomposition is what you need in order to identify the weights. And that's exactly the way some colleagues, Anand Kumar and others in 2015 went, and they went into the use of rank 1 decomposition of third order symmetric tensors. And that's the way they approach the problem. I want to show you that you don't need to go that far. You can stay with second order differentiation, and this would also allow you to have a slightly better somehow error estimates. And the interesting fact is that this technique can be extended even to 2 and deeper layer neural network. So you don't need to stay on the 1 layer neural network as it has been done by Anand Kumar and the others. So here is the theorem. The theorem tells you that if you have a shallow neural network with which is sufficiently smooth and the weights are linearly independent, then by using a finite number of samples of the network, you can construct approximative weights that are very close to the original weights up to an error epsilon that represent the step size that you use to do finite differences. Now we are talking about, in this theorem, we are basically focused on the active sampling. And this is done by certain randomizations as well. So the result is valid with high probability. And once you have the reached directions, basically you can reconstruct also the neurons. And so that's what you get here. So if you compare somehow our method with stochastic gradient descent or minimization of loss, what happens is that the error that is here indicated with red on the reconstruction of the weights by using stochastic gradient descent will never go down. So they will never be able to reconstruct the weights. Instead, our method, if you don't have enough information, you never reconstruct the weights, but all of a sudden you have a phase transition and you get basically exact reconstruction of the weights. Similarly, when it comes to the uniform error approximation of the network, of the entire network as a function, it turns out that the error of gradient descent will saturate at some point. It will never go really to zero, while we will have, again, this phase transition that tell us that we have completely reconstructed the network uniquely, basically, right? So that's what is coming into the game. Okay, how this technique work? The idea is that in a certain sense, well, I would like to really tell you more. So I would skip certain technicalities. In these technicalities, would be possible to reduce the problem from having m number of neurons that are smaller or equal than d to the case where d is equal to m. So I would skip this part because I see that the time is short. So I won't give into these details, but say after this part, we can assume without loss of generality that d is equal to m. And the idea is simple. Basically, you can learn the span of the AIs by querying multiple gradients. And if you have multiple gradients, basically you can learn the subspace A, and the subspace A is the subspace where things are happening because every input is taken as a scalar product with respect to the AIs. That is morally what is going on. So how does it work, this strategy of recovering the weights? The idea is to find a way to get an approximation of the span of the tensor products of the weights, okay? And once we have this tensor product, the next step is to prove that with this space, I'm able to find a linear map that would allow me to reduce the problem from the AIs being linearly independent vectors to the AIs being orthonormal vectors. So I can orthonormalize the problem. And once I orthonormalize the problem, I'm living in a space where the AIs, tensor AIs, are orthogonal matrices that are spanning the space A. And within this space, these are the unique extrema of the operator norm under the constraints of having the Frobenius norm less or equal than 1. So in a certain sense, we can take advantage of the geometrical property of these guys to be basically coordinate directions. And because of that, you can identify them within the space A, or actually in the space A tilde, as extrema of a certain type of problem. And the funny thing is that this problem is again non-convex, of course, but it's a much easier non-convex problem. So the problem of finding the AIs is non-convex, but differently by using a standard loss, we can, in a certain sense, make this canonically to be about a variational problem that is much simpler and on which one we can say a lot about the solution. Okay, how do we construct an approximation of the space A? Morally, what we consider is finite differences approximation Hessians, and then you can find, in a certain sense, the span of them, and by using singular value decomposition, or PCA, what the people call PCA, you can find a space A tilde or a projection A tilde that is approximating the one of the A. So in other words, it's not that difficult to get an approximation to A tilde. The whitening, this idea of orthonormalization. So if you had the space A exactly, and we had a matrix G that is a linear combinations of the AIs, but with a singular value or somehow spectral decomposition given by these lambda i's, we could use this matrix, okay, that we have to assume that is the positive definite matrix. We can construct a matrix W that pre-multiplied with respect to these weights, make them orthogonal. So this is a very interesting thing. So if we find the function a matrix G within the space A that is positive definite, then we can orthonormalize these AIs. What does it mean? It means that if I twist the input of the neuron, of the network by this matrix W transposed, then morally what I can do, I can bring this matrix on the other side, maybe modifying the neurons by scaling them in a suitable way, and obtaining that a new network whose weights are actually orthonormal. So if I have the space A, and I could find in this space G a positive definite matrix, then in a certain sense I can reduce my problem to be the one of finding a neural networks with orthonormal weights. Okay. So in general, we don't have A, but we have A tilde. I don't get into the details, but basically, nevertheless, it's possible to find a matrix G numerically. It's possible to query the space A tilde and finding within the space A tilde by suitable optimization, a matrix G will be positive definite, and you will have the resulting weights somehow that are whitened won't be exactly orthonormal, but they will be nearly orthonormal. Okay, so I don't get into the details, but basically that's the possibility that you have. And then everything is back to the problem of finding these extrema within the space A tilde that are optimizing the spectral norm under the constraints that the matrix that you are trying to find have Frobenius norm less or equal than 1. Okay, so this problem, we can analyze the problem and we can find first order and second order optimality conditions. So we can characterize very nicely what makes local minimizers of this program. And these conditions are spelled out here. I don't get into the details, but they allow you in a certain sense to have a very clear grasp on how the optima look like. And it turns out that if you compute local maximizers of this program and you consider their first eigenvector or singular vector, then you are going to be sure that this first singular vector will be certainly close to at least one of the ridge directions. Okay, so and you can iterate this problem by trying to find all the local maximizers, and once you have all the local maximizer, you basically have the result. And the way you do it is by testing the first and second order optimality condition with respect to the exact solutions, and try to see how this interplay with a local maximizer of the program. Okay, so right, I don't get into the details how you solve this program, but you can use a gradient ascent method, and this gradient ascent method would in fact converge really to local maximizer. Once you have the ridge directions, you do have the network, because again, it's possible to construct approximations row hat by querying the network in suitable directions, and this will allow you to reconstruct the network. Okay, I would like to give a glimpse how you move on into two and deeper neural networks. in two neural networks, in two layer neural networks, which is a barrier, mathematically speaking, because many results now in the literature are all about one layer neural networks, because it's difficult to analyze deeper neural networks. And here we have some results that are definitely going beyond this barrier. And they are about somehow, again, having two nonlinearities, rho and h. And then we have certain weights A and certain weights B. Okay, so we have two layers with each respective weights and each respective nonlinearities. However, we can combine the weights of the first layer A with weights of the second layer B and form a new set of weights that we call VL or V's that are in a certain sense entangling or somehow basically putting together these weights of the first and the second layer, and we call them entangle weights. And the assumption that we have is that the weights of the first layer together with the entangle weights that are basically again in the same space, they form a frame. A frame, it's a generalization of a basis, but it do allow redundancy. So they might be be redundant with respect to the dimensionality that they represent. Okay, this is a bit more or less the architecture and the assumption here. And interestingly enough, if we do the same game as we were doing before by considering Hessians, differently from the one-layer neural network, here the problem is that you don't have symmetric terms only. So you see that there is the AI, tensor AI coming into the game as it was happening for the one-layer neural network. But here you have also non-symmetric terms that makes your life pretty miserable, because in a certain sense, first of all, identification, even in higher order tensors, identification non-symmetric tensors or decomposition of non-symmetric tensors become an NP-hard problem. And definitely having somehow decompositions of matrices in non-symmetric terms of this type that are non-orthogonal, then you don't know how to do. But if you do some little algebra, you can rewrite also this part that appears as a non-symmetric in terms of symmetric vectors that we may call VXL. But the only problem is that they do depend on X. So if we sample multiple Hessians, unfortunately, we won't say in the same space. So they are not belonging to the same space because you are changing, in a certain sense, these basis functions or these basis tensors. And so you won't belong to the same space as it was happening for the one-layer neural networks. So the interesting fact, though, is that the function that maps X into VXL is Lipschitz. It's Lipschitz, you can control it. And what does it mean? It means that if you sample Hessians with a relatively concentrated distribution, it turns out that also these weights will be relatively concentrated. In particular, if you sample, say, X uniformly on the sphere or somehow concentrated around 0, then all of these guys can be concentrated around 0. So if we sample X1 and then XM around 0 in a certain sense, what you obtain is that all the Hessians won't lie in the same space, but they will be very, very much concentrated around one space that is about these entangle weights evaluated in 0. And so the idea is that, okay, now we have a space which is the span of this of the original weights, and then these particular entangle weights. And we can use again these optimization methods over matrices that I presented before to identify them. And then the problem will be basically to disentangle the weights And once you have the disentanglement of the weights, basically you have the network, okay? So this is a bit the idea. And the funny thing is that this idea can be completely generalized to deep neural network. So we have now published the paper on the one-layer neural network to this two-layer neural networks. And we are basically finishing now the paper on the deep neural network. So in the next weeks or couple of weeks, we hope to have the preprint online. But basically it's a bit the idea how this is working. And this allows us to identify networks uniquely by using a finite number of samples. So this is something that is far beyond what in the past has been considered. So the time is up, so I'm not really able to show you all the rest of the details. But I will jump right away to the literature. So if you're interested, we do have a first paper that is now appearing in Information and Inference, where we do attack the problem of the shallow neural network that I basically describe you in a very detail. And then there is a second paper by Klock and Raukensteiner and myself that is appearing now in Constructive Approximation, that is about the two hidden layer neural networks, and we will come up soon with a complete theory for the deep neural network. So with this, I would like to thank you for your attention. I hope that despite the fact that I did not indulge too much on my technical results, but I gave you also a little bit of overview of interesting results coming up recently in the mathematical literature about this topic could have been interesting and useful.
Okay, thank you, Massimo. Thank you for this very, very nice and exciting talk that brought us to the deep questions in neural networks. Now, for the audience, people can can pose questions to Massimo by writing in the chat. So I will monitor the chat, and you may convey questions to Massimo. In the meanwhile, let me just ask you. You mentioned the problem. Actually, there are not so many results concerning the identification of the dimensions of the layers, right? And as far as I understand, you have assumed in your analysis, in the analysis that you presented, that the the dimension m on the m1 and m0 or whatever is fixed. Did you get from your analysis some kind of intuition or some kind of perception about how would be, at least in this somehow simplified situation, the optimal choice, or some let's say quasi-optimal choice for the dimension?
Yes, so there are things that we think that we understand, and there are some other things that are probably need to be further clarified. So I was mentioning about the space W, right? The space W, you approximate it by considering multiple approximation to Hessians or something of the like, and then you perform a singular value decomposition of the vectorization of these Hessians. So the Hessians are matrices, you vectorize them, the vector is stuck into a matrix, you do the singular value decomposition. And depending on how the singular values are behaving, you would expect at some point they're dropping. And the way they drop is exactly at the point where you have, in a certain sense, the dimensionality of the space coming into the game, right? So this would tell you more or less how many neurons are really important in this network, okay? However, it doesn't tell you to which layer they are supposed to be. This is an information that you have to acquire once you know which are the weights. then you can query again the network to ask the network whether this particular weight belongs to the first layer or the second layer or the third layer and things like that. On this, we do have results that allow us to go up to the 3-layer neural network to try to completely understand the architecture up to that point. But we don't have a complete theory that tells us how to do it in arbitrary network. So deep network. So this is still an open issue that we are trying to find a solution. But it's an interesting problem. You pointed out to an important issue.
Okay. Let me see if there are other questions. Well, maybe waiting for some other contributions. Let me ask you something which is only indirectly related to your presentation, but I think it is of importance in evaluating the impact that neural networks and deep learning can have on other, let's say, other parts of scientific computing other than image processing. My very little experience with these tools says that if you, let's say, try to use what is available in the literature, which often comes from, let's say, software which has been produced, you encounter the problem of the accuracy of computations. Which is, at least in my opinion, in my experience, mostly confined to what we call in numerical analysis single precision. And the reason I think is that for image processing you don't need 15 decimal digits, and so let's say single precision is enough. On the other hand, if you think, for instance, of applying these methods to partial differential equations, accuracy may be an issue. So, namely, first-order accuracy, or let's say single precision accuracy, may not be enough in certain applications. So, in some sense, sometimes it seems that decades of numerical analysis and attention to precision have been somehow bypassed by these new tools, which I think is not true, but it's just a matter of choosing the right framework. What is your opinion on this, Massimo?
So my opinion is the following: that in a certain sense, there is the concrete feeling that these methods do have important features, and the people are in a certain sense trying to provide both numerical evidences and theoretical results. The theoretical results of the kind are the following: the people prove that the solutions of certain partial differential equations belong to certain classes of functions, and that these classes of functions can be very well approximated by neural networks. This does not mean that you know exactly how to compute the neural network that approximate the function. The typical thing is that would happen is that you need to use one of these famous or infamous optimization methods, right? So eventually you have to fit the neural network with respect to the PDE, and this is again a black box. So, and the result is often having these troubles of the saturation of error that you point out, And but this is again an evolution. So in my situation, if I know that the solution is a network of my kind, my method would compute it exactly, or with machine precision. Are you with me?
Yeah.
And so this is a bit the effort that is currently going on. So if I had a method that a bit breaks these barriers of saturation, and it's able really to identify networks in a very accurate fashion, then these kind of issues would be overcome. But the theory tells you that if you find the right network, the right network would approximate well the solution. This is really interesting, right? So in particular, because they observe that in high dimension, the curse of dimensionality won't be happening because somehow the space of solution is approximable by neural network without the curse of dimensionality.
Thank you, Massimo. Very clear. There is a question by Marco Viola concerning the costs. So he asked, how expensive are these identification algorithms in terms of time? Are there considerable differences in terms of quality of the network?
As I said, it is often the case that people don't care about the computational cost. And the reason is that, first of all, the evidence is that these kind of methods, optimization methods, they become good, or they become particularly good in a very special regime. And the regime is the one where the number of parameters of the network is larger than the number of samples, but for having very good results that basically show you that you have a relatively stable type of behavior of this network in certain tasks, like classification of images, or even somehow translations of text and things like that. The number of samples that you need to have is really exaggeratedly large, and the people don't care. People really say, let's throw into this machinery as much as we know in terms of data and in terms of parameters, and then we will use supercomputers. This is true in the sense that in Alaska, there are, in this moment, very big computing centers of big corporates, precisely because they simply say, well, let's use more computational power. There is very little interest at this point to really minimize the number of samples. To a certain extent, this idea of what can we do with a minimal number of samples with respect to the architecture is a problem that is perceived by many as an exotic problem where only mathematicians are really interested. But that's a bit the situation right now.
Yeah, we hope for the best in the future. Okay, so I think that we can stop here. Let me thank again Massimo for his beautiful contribution and for being here with us today. And let me call our president for the conclusion of this day.
Okay, I hope I am on.
Yes.
Yes, okay. I don't see me, but I think it's time the time has come for a final word, and I'm very glad to be able to just to say goodbye. And first of all, I would like to express my personal gratitude and the gratitude of everybody who have been listening yesterday and today, the speakers. I like to mention them in the order of appearance. I thank Giuliola Staffilani, Michalis Dafermos, Nuria Fagella, and Massimo Fornasier for their beautiful talks. I should say more. They not only gave us 4 beautiful pieces of mathematics, but they really made an effort to make us participate in these beautiful pieces of mathematics. It is clear that there were risks in this kind of initiative. Having to speak to a computer, to a camera, and not having people around you and in front of you is hard. We all are discovering how hard it is. And it is clear that it was an experiment. And if it was an experiment, I think it was very successful. I must say that I really checked. The number of people who got in touch with the INdAM Day grew also after the talks. People just got in touch with the YouTube channel, and really hundreds of people have been connecting to this initiative. And I really think, I like to think that it is a sign that we are sticking together on what we like the most. And in this way, we are trying to formulate the best wishes for the next future. And I'm sure that we will have chances to get together, but somehow, I'm not among those who think that we should adjust to a small camera in front of us and just get rid of personal relationships. No, we should get together, but somehow we are trying to get the most out of this. And I really think that this is the best way to, well, to exchange best wishes for the new year and for mathematics in general, and for this holiday season and for everybody. Just a final word again, somebody mentioned it. All this would not have been possible, first of all, without the effort of the scientific committee and of the vice president who made possible the invitations and the scientific coordination of the INdAM Day, but without the effort of the administrative staff and who made, it seems easy, but it's not that easy to make all this happen. So thank you all very much. And what should I say? I would say goodbye, and hopefully next INdAM Day all together someplace in Italy, and we'll try to make it happen. Thank you very much.